Okay, let me first thank the organizers for having the great sense of organizing this workshop in sunny California while it's raining dogs and cats in Lausanne. So it's a pleasure to be here, and for many other reasons too. Good. So I picked this talk because actually last year ago, quite a few of us were here at Science Institute for a while. That's Henry Pfister and his student Santosh. That's Srinivas Rüdiger and Marco Mondelli and Aaron Sasson, and we were actually all here. And it turned out that actually two groups worked on the same problem, namely Santosh and myself with these people here, and we actually arrived at the same result, so we put it together. And so that's what I'm presenting is now the joint work which was done last year at the Science Institute while we were here for a couple of months. Good. Now, what I'm talking about is coding and the very standard setup. So just since the first talk on this, I have simply some source, and I'm thinking here of just bits, IID bits, and I'm making what's called a block code out of this. So I'm making vectors of length n out of this, and I send it over channel, and this channel acts just bitwise, so the simplest possible channel can you have. And either the channel might flip certain bits, or it might simply, and that's what we're mostly going to talk about, it might hide certain bits, which is called the binary erasure channel. And at the receiver, we see this perturbed block, let's call it y, and the task, of course, of the receiver is to figure out with high probability what was actually sent. So we have the code word, it's perturbed, and the task is to recover it with high probability. And so typically our setup is that we're thinking of block code. So these are n tuples, and these might be, the code is a very simple, trivial example, of course. And our task will be to do this with high probability. Now, in communications, really all we care is about this particular figure. So let me just try to explain it. So we have typically not just one family, not just one channel, but we have a family of channels. So for example, in this case, it's the family of binary erasure channels, where this parameter on the horizontal axis is the erasure probability. So few erasures. So for example, in this case, roughly 35% of the bits will be hidden from you, versus here about 55% will be hidden. And so typically we think of having here some good channel, and progressively as we go to the right, we have a bad channel. And then for a particular code, what we worry about is really the probability of error. So how often, what's the probability that we actually can recover? And there are two kind of versions. Either we worry about recovering the whole block, or we worry about recovering the whole bit, and I'll talk about both of them. And so then the typical scenario is that we have one other parameter, namely that's the block length here. And so when you look at these curves, these are the curves for various block lengths, let's say maybe 500, 1,000, 2,000, etc. And if we're talking about a good family of codes, then what should be true is that these curves should approximate a jump here. So there should be a phase transition here, and this point should be exactly, it's a specific point which has only to do with the rate of the code, and that's the Shannon capacity. So we know that if I want to transmit reliably over a particular family of channels, and I want to do this, let's say, at half a bit per, half a bit of information per bit that I'm sending, then depending on this channel here, there will be a parameter here which tells me that below this I can do it. There are systems that can do it, but above this, above the Shannon limit, I cannot do it. There's no code. And the hope is, of course, to construct codes which approach that as a function of n, and do so efficiently at low complexity. Now, traditionally, if you look at all your cell phones, your disks, etc., and you look in there, then what's in there is typically these kind of codes. And these are codes and graphs which fit very well into the picture that we have been talking about. So instead of thinking here, let's say we have talked about KSAT and we have talked about the Fetker graph, it's very similar. For us, a code would be described, so these are the bits of the code. In this case, it's a trivial case. It's like just 3 bits that define the code. In practice, this would be 1,000 or 10,000 or even 1,000,000. And then the code is defined by adding certain constraints to it. So in KSATs, there are certain constraints. For us, these are typically linear constraints, so just XORs. And the code is defined as the set of all these bits, vectors of length n that fulfill these linear constraints. So in this case, I have 3 degrees of freedoms to start with. I take away 2 degrees of freedom because I have 2 linear constraints. So there are really 1 degree of freedom in here. So there's really just 2 code words that, in general, that would define the code. And the standard picture, and that again fits very well with what many people already have talked about, is the standard decoding is what Gallagher had introduced, namely message passing. Okay, so you start with the received thing. So for example, here it's for the erasure channel. We're starting with a certain bit sequence, but some of them are erased. And then we are sending back and forth by message passing these messages using the local constraints in a greedy fashion and hope that we actually converge to the right limit. Okay, so these are the codes and graphs. They're known as either low-density parity check codes, turbo codes, many other classes codes, and that's pretty much what you have in any real system that you have right now.
Question: in an erasure code, in an erasure channel, when you've lost a bit, do you know that bit is missing, or
yes?
Do you just
So
fewer?
right, so that the two kind of, or the three most important channel models is the erasure model, in which if you lost it, then you don't just get zeros and ones, but you get 0 and 1 and a question mark, and there's some physical property that tells you something went wrong. In the binary symmetric channel, it simply gets flipped, but you don't know. You might know the probability of flipping, but you don't know where. And additive white Gaussian noise channels, in which you get a real number plus some Gaussian noise. Okay, so these are the three most important models, and then many of the more complicated real models are just built up by making kind of combinations of these things and so on. But if you understand these three, you understand pretty much the picture. So codes and graphs fit very well into this. It fits, how do you analyze these things? We already had several talks about this too. Well, if you do message passing for codes, it's relatively simple. Andrea had talked about the density evolution, and if you analyze density evolution for these codes, then this tells you exactly what under message passing you can do. And then you can also ask what the ground state is, and that's what actually optimum decoding would do. And as we have heard now in many other talks, there's typically also a gap, meaning if you take such a type of code, there would be something that you can do efficiently on the message passing, and there's something that you can do if you had optimum decoding, maybe map decoding, and then there's a third limit, which is the absolute limit, the Shannon limit, and the hope is that with the efficient algorithm, you get as close as possible to this Shannon limit. So that's the name of the game. Okay, so as I said, that's pretty much the standard that everyone is using, but that's not what I want to talk today. So the history is kind of interesting. In 48, when Shannon defined capacity, there were not really any codes around, but then very soon there were codes defined, namely Reed-Muller codes, Reed-Solomon codes, BCH codes, and they were very nice in that they have a lot of structures, a lot of algebraic structure, and I'll tell you a little bit about it. So it's the opposite of random. And these were beautiful codes that have many nice properties, and they were used for some space exploration and so on, but they don't get you very close to capacity, at least with the decoding algorithms that people knew at the time. And so then over time, other classes of codes came along, so in particular, low density parity codes, and now we have also things like polar codes, etc. And so these codes kind of were forgotten, okay, and people really didn't talk so much about. But as it often happens in history, history repeats itself, and as I'll try to tell you now, that these codes actually coming back with a vengeance and become again very interesting because of some new developments. So what are these codes? So this is Muller and this is Reed, and in 54, I think they first Reed defined the codes, and then first Muller defined the codes, and then Reed defined the decoding algorithm. And they were quite popular in the 50s. If you look at typical textbooks in the 60s and 70s, the whole chapter's dedicated to these kind of codes because they have very lots of symmetries and nice properties, and I'll tell you a little bit about what these properties were. So now, they were, as I said, pretty much forgotten then for a while, and there were only a few people that worked on it. This is Ilya Duma, who, for the last, 10 or 15 years has consistently still worked on these kind of codes, but, it was not a particularly hot topic either in communications or in computer science for quite a while. Now, why are people now back interested in these codes? Because in 2008, there was another class of codes defined, which are called polar codes. And it turns out that polar codes are the first class of codes for which we can prove that they're capacity achieving under low complexity coding algorithms. You know, low density pair check codes and so on before were known to be very good, but there was like a proof missing. It's only very lately that we have actually found a proof for that. And so, you know, they have many, many nice properties, very, you know, universal, lots of applications. So they were quite, you know, stirred quite some interest, even for current, you know, next generation wireless systems. And it turns out that these codes are actually very related to Reed-Muller codes. And so since now, you know, people discuss that polar codes are very good, you know, people try to go back and say, maybe Reed-Muller codes, in fact, in the 50s were also excellent. Maybe we just didn't know about it. So let me just tell you a little bit what the connection between these two types of codes is. So look at this matrix here. So this thing here just represents an, in this case, 8x8 binary matrix. And you know, it's just, you just think of it that you put in here zeros and ones, and you send it forward. When you ever have a node like this, simply both of these, you know, it sends the message forward, both of them, and you have something like this, then this is simply the XOR. Okay, so this is just a matrix multiplication with whatever vector u you have. And so think of this as the information, and think of this as the code word here. Okay? Now, it turns out that this is an n by n invertible matrix, so that itself doesn't form a code because it would have rate 1. There's no redundancy put in here. But it turns out that it can do the following. At the decoder, you do the following. This is the channel. And so each of them goes for an independent channel. You observe the observation y here. And you do what's called successive decoding. So you try to figure out what u0 is, given the whole observation here, and assuming that you know nothing about these. So these are simply IID bits, okay? And that turns out, if you untangle it a little bit, that if you look at what this is simply a tree, you know, an inference problem on a tree. And so message passing is optimum. So you can just simply send the messages up there, and you get some probability of error for this bit. Okay, so let's assume you could actually do this. So imagine this again, not 8x8, but let's say 1,000 by 1,000 matrix. And so let's assume you could figure out what this bit here is. Then you go simply to the next bit. Okay, so the next bit is here u1, there's a particular order, assuming that you already have u0. And again, it turns out that this is simply the inference problem on a tree. You can do this efficiently, and you simply go down, you know, as in a certain order. Now, yes?
So the little nodes are XORs here? These are like
these nodes are XORs, these ones, and these are simply repetitions. So you simply repeat whatever you have, and you send it in both paths. Okay?
Okay. So these are like controlled NOT gates in a certain.
Yes. Okay. So what you get is actually, you get repetitions and you get XORs when you look at the tree. Okay, so in the tree you have layers where you have XORs, and you have layers where this corresponds to repetitions.
So this whole thing is like a 2 to the 8 by 2 to the 8 matrix over GF2.
Yes, so this is always, in this case it's always binary for the simplest version, and you should think of this as maybe 1,000 by 1,000 matrix here. Okay. Now it turns out that, and that's the kind of the miracle of polarization, that independent of, you know, with high probability and independent of what you're actually, you know, sending here, there are certain positions which you can almost always decode. Okay, so you can decode with high probability, and there are some other positions here which you can essentially never decode. Okay, so it completely polarizes to either being almost certain to be able to decode or almost certain to have zero knowledge. Okay, and the other miracle is that exactly, you know, if whatever the capacity of this, let's assume the capacity of this channel is a half, then exactly half of these positions would be perfect and half of the positions would be useless. And so then the code is very simple. You simply pick these positions which are perfect. Let's assume the blue ones. You put the information in there. You pick those positions which are useless. You put zeros in there. Okay. And so now you simply take this bit, encode it. That's your code word. And now you go down this decoding order, as I said. But if it's a useless channel, okay, you already know on both sides that's a 0, so you can decode perfectly because it's already agreed upon. And if it's a perfect channel, you can decode by definition. Okay, so that's kind of how the code works. Now, what's the relationship to Reed-Muller codes? Well, it also, you know, uses this matrix, but it makes a different choice of which of these positions is picked as information and which of these positions are what's called frozen. And what is the choice there? Well, for example, let's assume that all of these things are 0 except the last bit is a 1. Okay? If you go through it and chase down, so the 1 will come out here, but the 1 will also flow here and will go down here. And if you chase it down, you will see that if, for example, you set a 1 here and everything else 0, all of these positions will be a 1. Okay? So this gives you a maximum weight 2 to the n code word here. But for example, up here, okay, I guess if you chase it down here, this will be a 1. and I guess that's the only one. Okay, so there's some position that give you a lot of ones, and there's some position give you a few ones, and since this is a linear code, you know, the weight and the distance between code words, that's the same thing. So what you do for Riedmüller codes is you simply pick those positions here that give you code words out here that have maximum weight. Okay, and that guarantees that the set of code words, if you're looking at the separation between two things, has maximum separation. And it turns out that this distance between, if you do that, and if you pick a rate that's somewhere between 0 and 1, it turns out that the minimum distance of the code words implied here is of the order square root of n. Okay, so that's in general much better. I mean, also for polar codes it's square root of n, but the constant by definition is better here. Okay, so these are codes that kind of maximize the weight, versus the other codes are codes that somehow work for this polarization thing. Okay, so if you try it out, okay, so if you simply simulate things, then it turns out that actually Riedmüller codes are significantly better than polar codes. We know that polar codes already achieve capacity, but that the speed at which they achieve capacity, so in other words, the length that you need in order to have a certain error probability if you're transmitting at a certain gap from capacity is much smaller. Okay, so this is just a simple example here. This is again a binary ratio channel. This is the error probability. And as you go from left to right, you basically start with a polar code, and then you end up with a Riedmüller code. There's kind of an interpolation to go from one to the other one. And it turns out that at least for this experiment, this is what random codes can do, which is essentially the optimum thing. You can see that Riedmüller codes are actually very, very good. Okay, so the question is, you know, if they're so good, perhaps we should actually use them. But before we can even use them, we should know basic things about them. And the first question that we should know about them is whether they're even able to achieve capacity, right? It looks pretty clear that they should. They look better than polar codes, but you know, it's not like we actually know. And indeed, as I said, this was an open problem in the Simons Institute last year when we were here, and two groups started working on it. And I'll tell you just right now, you know, how this story unfolds. So now we're not the first to ask this question. In the 60s already, people had come up and, you know, asked this question whether Riedmüller codes achieve capacity. And there were several other references we could find in the literature. But much more lately, you know, three people. This is Emanuel Abbe. This is Avi Wittgesen and Amir Spilka have looked at that. And they found a very nice proof that indeed these codes achieve capacity. But you know, this is in a particular regime. Okay, it's in the regime where the rates either go to 0 or to 1. Okay, now in computer science, this regime, you know, can make perfect sense. The applications for codes in which, you know, the capacity or the, you know, the rate itself is not the deciding, you know, deciding thing. So that was a very nice result. But let's say if you want to use codes for communications, right, you want to fix a particular rate. Maybe it's a rate 0.1, maybe it's a rate 0.9, depending what the channel is. And so what I want to show you now is that yes, indeed, they achieve capacity, you know, just for the simplest case, the binary ratio channel, but it turns out it's indeed for all rates between 0 and 1. Now, you would assume that, you know, typically when you look at codes and you try to prove anything about, you would assume that you need to know a lot about the details, right? I haven't told you, you know, much about what this code really is. I've told you, you know, it's this matrix, you're picking certain rows, but I haven't really told you much about the details of the code. And you would assume that the next thing, you know, I have to tell you now a lot about the structure of the code, properties, maybe the weight distribution, other things. But it turns out that actually we need to know almost nothing about the code. Okay, so there's only a single property about the code that we need to know. And this property is that this code has a high degree of symmetry. And I'll tell you what it is. Okay, and indeed, whatever I tell you now has actually nothing to do with per se Riedmüller codes, but simply the crux of the matter will be that any code that's highly symmetric will actually achieve capacity. So symmetry is enough to be a good code. So there are three ingredients. Codes are highly symmetric. Then I'll tell you something about that's, you know, mainstay of theoretical computer science, about symmetric monotone sets that have sharp thresholds, and something that's actually came out of analysis of iterative codes or codes on graphs, which is called the area theorem and exit functions. Okay, so the first one, it's very easy to dispense with, and this is, you know, there are many other papers, but this paper is already in the late 60s by Kasami, Lin, and Peterson that proved that these Riedmüller codes are highly symmetric. So let me just tell you what kind of symmetry that we need. So again, this is a very simple example. I just show you graphically. Let's assume you take all the code words of the code. In this case, it's just length n, and I guess maybe rate a half or something like that. And let's assume you put them all as rows. Just write them out of rows. So these are zeros and ones. The zeros you can see very properly. So what does it mean for code to be one transitive? Okay, it means something very simple. It simply means that no column in here plays any special role. Okay, that you can find a permutation that maps any column to any other column. Okay, so for example, so you tell me, for example, that you want to map column 1 to column 3. Okay, then the game is that I have to find your permutation on the index set. Okay, so from 0 to 8, such that this permutation carries column 1 to column 3, and for the rest it's completely free. Okay, we don't care, we don't worry about what it is, but you have to find me a permutation, and this permutation has to be in such a way that the set of code words stays preserved. Okay, so the code has to be invariant under this permutation. Now if you look at these rows, it's no longer exactly the same, but that's simply because the rows themselves have shifted too. Okay, so if I simply shift the rows, then you can see indeed that the code has stayed invariant. Okay, so one transitive simply means that if I look at the automorphism group of the code, so I mean I look at the set of permutations that keep their code invariant, okay, then there's at least one transitive. For every index I can find, and j, I can find a permutation that maps I to j into this automorphism group. Okay. Now, if you know what one transitive is, then it's also pretty clear what two transitive is, right? So now I can simply ask for two conditions, right? As long as these conditions, can be fulfilled. So, for example, column 1 must be mapped to column 3, and column, let's say 8 must be mapped to column 4. Okay. So for any such pairs, you have to find me again a permutation, again that maps these columns into it, and it keeps the code invariant. Okay. And so all we are saying now, and that was already proved in '68 by Peterson and et al., is that Reed-Muller codes, among a class of codes, not the only codes, are codes that are two transitive. Okay, and that's the only property that we'll actually need for these kind of codes to prove what we want to prove. Okay, so that's ingredient number 1. Now, again, right, what we want to show is that these codes achieve capacity. So it means, remember these curves that went down, these probability of error curves, and when the length becomes large, these should become jumps, and I want this jump to happen at capacity, right? So that's really what I need to prove. So what we need a tool is to show that certain curves or certain functions have sharp thresholds, and so what we use is a very, very basic tool. Basic in the sense that it's very, very useful in theoretical computer science, probably physics too. And this tool goes back to a set of people. I guess I have to picture it a little bit later on, that prove that certain functions, as the n, as the block length, or as the set or the dimension of the function goes to infinity, exhibit sharp thresholds. So let me just tell you what is this setting that I consider here. So we are working on the Hamming cube, so 0, 1 to the n, and let's take a subset of the Hamming cube, right? So some subset of the 0, 1 vectors. And what it means for such a set to be monotone, it's just, I guess in math, this is called an upper set or an upset. It simply means that I have the natural partial order on the vectors of 0, 1, right? In which I simply component-wise compare things. And now I'm saying that omega is monotone, that if an element is already in the set, right? If I have an element in there, then anytime I'm adding extra zeros, so extra ones, so I'm flipping a 0 to a 1, so I'm making it larger in the partial order, it also has to be in here. Okay, so that's all we're talking about. So I have, this is monotone. If I have an omega and omega prime, and this is larger in the partial order, and the omega prime is already in there, then the omega also has to be in here, right? So a very natural property for a set to have. Okay, so that explains what's monotone. So for example, if you look at this set here, if you're looking at it, for example, this vector is in here. So if I flip this 0 to a 1, then this must also be in there. And indeed, we have this element also in here. But if I took out, for example, the last one here, this set would no longer be monotone, right? Because it's missing this one here. Okay, now the next thing is I need to explain what symmetric is, because we need monotone and symmetric sets. But that's very easy because I already explained it. For omega to be symmetric, means exactly what I have described beforehand, namely it must be one transitive. Okay, so again, it's just a set of vectors of length n, right? And again, I want no column to play any special role, so it simply means that there must be, again, a permutation for every I and j that maps I into j. Okay, so for a set to be symmetric simply means it must be one transitive. For example, if the set was cyclic, right, so if I could cyclically shift it and it would stay invariant, then that would be one transitive. Okay, so I have monotone and symmetric sets. If you look at that here, this is symmetric, but for example, if you took this out, it would no longer be symmetric. It's easy to see, because this column has a 1, 0, and 1, but this column has a 1, 1, 1, so there's no way that I can map one column to the other one, and it would stay preserved, right? Okay, so now we have monotone and symmetric sets. So let me now just put a probability on this set. So I just put the standard Bernoulli product measure on this element. So meaning take any element in here, right, and simply assign to it the probability, which is epsilon, which is a parameter between 0 and 1, to the weight of this vector here times 1 minus epsilon n minus the weight, right? So clearly that forms a probability distribution on this whole Hamming cube here. And so then naturally, if I have now a set, I can define the probability of this set as simply the sum of the probabilities of the vectors in here, right? So I have a notion of a probability of this set here, omega. Okay, now what will this, this set be for us? Well, it turns out that this set later on will be for us exactly the set of erasure patterns. Okay, so think of an erasure as a 1, think of non-erased as a 0. Then this here will be exactly the probability that we get an erasure pattern that falls in this particular set omega. Okay, and so this set will have a particular meaning. Okay, and so now, as I said, this goes back. There are many versions of this, but this is Calais, Friedberg, and Bourgain, and we're using a particular version of theirs. So, and what does the version says? It says that if you have if omega is monotone and symmetric, right, and you're simply plotting the mu of omega here as a function of the epsilon, right? So you actually, so this is the epsilon here. Remember that this probability depends on epsilon. Then unless this function is completely constant, for example, if you take omega to be the whole set, or you take omega to be an empty set, right, then it will be either the 0 function or the 1 function. But if it's not trivial, then it will have a fast jump here. Okay, so the width of this transition here is of size 1 over log n. Okay, so you have if n goes to infinity, you simply get a jump of this function. And so this will be important for us. Okay, so we need, before maybe move on, so we are not the first one that used these kind of ideas. There's Gilles Zemmour and Jean-Pierre Tillich, who have used these kind of ideas in coding theory in a very beautiful paper that shows the following. If you take any linear code and you either transmit over the BC or the BSC, and you look at the block map, so the optimum probability of error under the optimum decoding, then it turns out that this probability of, that you decode correctly versus incorrectly, so 1 would mean everything is incorrect, 0 would mean everything is correct, that this probability of error as a function of the channel parameter here has a fast transition, and actually very fast. It's 1 over the square root of the Hamming distance. Okay, so you pick any code, and this has a particular Hamming distance. Okay, so what's the maximum that this Hamming distance can be? We know that as a function of n, this Hamming distance can be a small constant times n. Okay, it can be linear in n. So this means, you might have a transition as fast as 1 over square root of n. And that's essentially as fast as it can be, because just the transitions, just the uncertainty of the channel itself shows you that even if the code was completely optimum, you would have a smoothing out or like a smearing out of this transition of 1 over square root of n just because of the variations of the channel. Okay? So if you have here a code that has an optimum Hamming distance, then this is a very, very strong result. And we have used nothing about the code other than it's linear and the fact that it has a good Hamming distance. Okay? So that is a very beautiful result. The only problem is that, similar as if you look at, for example, concentration results, where you can prove that, let's say, a function is concentrated, also here, it doesn't tell you anything where this transition actually happened, right? It simply tells you that there's a jump, but, this jump could be here or the jump could be here and has nothing to do with the rate. The parameters that you care about do not enter in here. So the question is, we want to kind of get this kind of result, but we want to have it in such a way that we can determine where this threshold is, and this threshold better be at capacity, right? That's what we want to actually show. Okay, so we need one extra ingredient here. It's something that actually comes from analysis of iterative codes. And goes as follows. So let me give you first a trivial example. Let's assume we have n bits here, 1 to n. And let's assume there's a single relationship in here. So you can think of that the first n minus 1 are freely chosen, and the last one is simply the XOR. Okay, so this is what's called a single parity check code. So it's the simplest of all possible codes that you can think of. And let's assume that you're sending now these bits over a binary erasure channel with a raised power of probably epsilon. And you get the observations here. So some of these might be erased, and some of them are whatever, you get whatever you sent. Okay, so now the yi's now are still whatever you sent, but there's an extra erasure probability. So now, what would be the optimum estimator if you wanted to estimate, let's say, bit I, and it's the optimum thing here, right, given that you have this observation here, right? Well, let's do the following. I'll do the optimum estimator, but I don't allow you to look at the bit itself. So this tilde I means you can look at the whole vector except the bit itself, okay? If the bit itself is received, then there's no question. It's exactly that bit. That's the erasure channel, right? But the interesting question is, what is if the bit itself is not received? So this is the optimum estimator in which you can look at everything except the bit itself. So the optimum estimator for bit I. And it's fairly clear what this should be. Well, if any of the other bits are erased, then you can't see anything because it's the XOR of the other bits. But if there's an erasure in here, right, then this could be equally likely be 0 and 1, and you don't know anything. But if all of them are not erased, then it's just a sum, right? And so that's the optimum estimator here. And so then what is the probability that you cannot determine the bit, that it's erased? Well, it's just 1 minus the probability that all of the other guys were actually received, right? That's fairly clear. And if you now do a trivial calculation, you integrate out this function here, this probability of error, as a function of the erasure probability, and you plot this curve here, you see that this gives you n minus 1 over n, but this is 1 minus 1 over n, but that's exactly the rate of the code. Okay? So now this is a trivial example, but it turns out that this example is, generalizes. So no matter what code I give you, if I'm plotting the probability of the average probability of error, determine the ith bit, looking at everything except the ith bit, and I average it out over all the components of the code, okay, then it's not very hard to see, and I'm plotting this curve, and I'm integrating this out, that this is always equal to the rate of the code. Okay, so this is an invariant of the code as you have invariance in physics, right? So it's a nice quantity. And it's exactly this property that we will use, and you saw flashing the proof. It's not very difficult to see why this is true. Okay, so this is called, this is the proof. Doesn't matter now. I'm not going to go for the proof, but it's just a few lines. Okay, at least for the erasure channel, it's fairly simple. For general channels, it's quite a little bit more complicated, but it doesn't matter right now. Okay, so if you believe that, first of all, this goes back to people that first looked at it is Stephen ten Brink, Gerhard Kremer, Alexei Ashkemin. This was for the binary erasure channel, and for the general channel, this was some joint work with actually Andrea. Okay, so this is true for the BC, but it's also for the proper quantity, which is not exactly the one I showed, but for some proper generalization, it's also true for general channels. Okay, so now we have all the ingredients that we actually need. Okay, so we want to put things together. So again, let's remind ourselves. Codes are highly symmetric. Monotone symmetric sets have sharp thresholds. Okay, and we have this funny invariant of a code, which is called the area theorem. Okay, so whatever curve you plot this curve. These curves can, so that you have to think of the area theorem that there's not good or bad codes. They're simply codes that have different characteristics as a function of the channel. Okay, so some of them have steep ones, some of them have flat ones. But if you look at the kind of the total gain that they give you over the set of the whole channel, it's always the same. Okay, it's just some of them are better at some values than other ones. So there's no codes for the same rate. They are in some, you cannot compare them if you want to compare with the whole range. Okay, so let's put things together now. Okay, so it's kind of clear what I want to do, right? I want to apply now the sharp threshold results to these particular exit functions, right? I want to show that there's a sharp threshold, and then I want to use the area theorem to determine where this threshold actually is. Okay, so let's do this. So, so we have this set. So we have now a particular code, I mean these Reed-Muller codes, okay? And now it turns out that these codes, since the codes are linear, and the binary ratio channel is what's called symmetric, which simply means there's no preference between 0 and 1. It's completely symmetric. And here, it doesn't matter what actually we sent, okay? So it's independent. The analysis we can do, assuming that any particular code word was sent, and so in particular what we will assume is that the 0 code word was sent. And so the only thing that we'll see is actually the pattern is either zeros or erasures. Okay, so all we look at that, and instead of an erasure, I'm going to write now 1. Okay, so 0 means it's correctly received, erasure means it's incorrectly received. And so what I'm going to look at is now for this case is I'm going to look exactly at this decoding function here, and I'm asked when is it incorrectly done, and I'm going to look at this particular function. And so what will happen is that if I'm looking now at my set omega I here, then this is simply the set of all those erasure patterns that cause trouble. Okay, so what I do is this: I have the code. I now send the code right here, and there will be particular erasure patterns that I have, and I'm going to look for each erasure pattern whether I can decode the ith bit or not. If I can decode it, it's good. If not, I'm going to put it in the set omega I. Okay, and since my decoder is defined that I'm not looking at the ith bit itself, this set is only over dimension n minus 1. Okay, I'm not looking at the ith bit itself. So this is a set, and so let me just skip it, but it's fairly clear. So what do we want to now do with this set? Okay, we want to prove that it fulfills these conditions that we have for the decoder, right? We want to show that it's monotone, that it's symmetric, right? And then we can apply our analysis. So what is the characterization of this set? Well, a pattern, an erasure pattern omega, will be in this set if and only if the following is true. So let's assume this is my pattern of erasures. So this position was fine. This position was erased, fine. This one we don't looking at because the ith position, etc. So this one will be in capital omega if and only the following is true. There exists a code word C that is dominated by this erasure pattern, meaning whenever I have a 1, there must be a 1 on top, okay? And it must have a 1 at the position I, okay? Now, why does this cause trouble? Because if I have this is all I see, right? These are the erasures. What I see will be this pattern here, right? And because I see only this pattern, I cannot distinguish between the all 0 pattern and the pattern that actually has 1 at these positions of the code word, right? And so, since the code is linear, what this will mean is that no matter how many code words I have that have, let's say, a 0 at position I that are compatible with received information, I have exactly the same number of code words in there that have a 1 in this position and are compatible with the received information. Since everything is uniform, they all have the same probability, and if I'm looking at the optimum estimator, it's simply a tie. Okay, so I don't know which of the two it was. It's equally likely to be a 0 and 1. Okay, so this is the characterization. And so now just note the following. Since we defined this set to be the set of bad erasure patterns, if I'm now taking this probability that I defined beforehand, right, that's exactly what the channel does, right? It's on each bit flips or not flips with probably epsilon 1 minus epsilon. Then this function here on the set, right, is exactly my probability that I cannot decode, right? And so I can, it's exactly this function here that is my probability of error, okay, that I cannot decode the ith bit. And if I average this over all the positions, that simply will give me some average curve. Okay, so now we want to show that it's monotone. It's too transitive, and so we want to just show that these properties are true. So let's just check the first property. It's monotone is very clear, right? If I have an erasure pattern in which I cannot determine the ith bit, if I'm adding an extra erasure in here, right? So I'm still hiding one extra one, then clearly this cannot help, right? You can see this slightly more formally. If for this erasure pattern I have already a code word that is covered by those things, if I now turn, for example, this bit also in addition to be a 1, right, then clearly this still covers it, right? So clearly it's monotone. Okay, so that's easy. What about, I want this set omega I to be 1 transitive. Remember, it should be symmetric, so it has to be 1 transitive. So what about this one here? Also not difficult. Remember, the code was 2 transitive, and I claim that that implies transitivity. Why do I need the code to be 2 transitive and not just transitive? Because there's one position that I fix. And this, when I'm looking for a permutation, this permutation has to carry position I into position I, and then I still have this my second degree of freedom that carries it here, right? So 2 transitive to the code gives me 1 transitivity of the set omega I. Okay, and then the last one tells me that that actually we have now always these positions, we had always these sets omega I, but because of the transitivity of the code again, all these sets are actually again the same. Okay, they're just again permutations of each other, so that's what I just called it's independent of the position I. Okay, so this means if I put all these things together, if I'm plotting this function here, which is, hi is now the same for each of them because these are all the same set, so it's just the sum itself. Then if I'm looking at that, right, I've put everything together, then this shows that this function here, by Friedgut and Kalai, must actually have a sharp threshold with 1 over log n. And so that's fine. But now if I'm using finally the area theorem, right, then this tells me that this thing here must be the rate of the code, but that's a 0, 1 function here. So it means that this position must be exactly 1 minus r, and that's exactly capacity. Okay? So this shows that indeed these codes in the limit achieve capacity. Just to wrap up, historically there's several ways of proving that codes achieve capacity. Right? For random codes, typically you look at weight distribution and that fulfills it. For codes and graphs, you look at, as we said, dense evolution, and then you carefully design graphs and do the graph structure. For polar codes, that kind of follows from the chain rule of mutual information. And what I'm saying here is that if you look at structured codes, if they have enough structure, namely symmetry in here, then just symmetry itself guarantees that they achieve capacity. Maybe just some extensions. There are many other classes of codes that have this property, and they're listed here. I talked about right now the bit error probability. You can also deal with the block error probability by either using a slightly stricter form of this monotone function theorem, or by looking at weight distributions. You can look at source coding, falls like this. And two works I've not been involved, but my co-authors have involved. You can look at quantum versions, or some even carried on beyond like just two transitivity and use the same kind of ideas. Good. So now that's the end of what I say. Just maybe 2 words. What would be really nice now is to extend this for general channels. There's still some bottlenecks which we don't know how to solve yet. I think the same proof should work, but we don't know exactly how. And then all this is still just the first step. This simply proves that these codes are very good. But we still need, and hopefully some relationships to polar codes would help there, is to show that indeed you can also decode them efficiently, right? It's one thing to say that these codes are very good. It's another one to find an efficient algorithm, let's say linear, or at least maybe quadratic or something, or n log n, that can actually do the decoding up to this limit. Good, and that's the end for me. Thank you very much.
All right, we have probably time for one question. That's very good. But I have a question. So, okay, when I started to learn about all this from you, actually, a few years ago, I remember, it was the big deal was to try to achieve capacity, and now it seems that there is a profusion of code achieving capacity. Polar codes and
right, but they're not all the same they're the same in the limit, but if you look at what codes actually use, you want to have it short length, right? So for example, polar codes are beautiful because they have nice properties, all provable, but if you look at the block length, it's roughly the square of what you should be able to do. Okay, so if you look at a block length, you transmit a certain gap to capacity at a fixed error probability, and you look at what block length is required, it's roughly the square of what optimally you should be able to achieve. So finite length scaling. So the hope is that actually the Reed-Miller codes might actually have the optimum finite length scaling. So if you could actually get an algorithm that works, this would make a big difference still.
Right. I've got one. Shorter blocks mean that the ramp up is in fact a slope up. I remember from studying finite size scaling of phase transitions that there's a good deal of theory one can go to understand how that ramping up occurs. Are you starting to look at that?
So we looked for all other codes, we looked exactly at that, and that's where, for example, for polar codes it comes that the block length you need, if you reformulate it, is roughly, so you need roughly n squared of the optimum block length that you would need if you had, for the best codes that exist, exactly through this finite length scaling. So if you're looking at, for a certain, you fix the probability of error, and you're transmitting at a certain gap from capacity away, and you're looking at how these curves approach the, this gap, okay, then you see that the block length is roughly n squared, okay? And
so there's a critical exponent there of a half?
yes, yes, that's exactly half. So it's the standard scaling that you see. We have done this also for LDPC and other codes. There it turns out that you have the best exponent, but it doesn't scale to the actual capacity, but it scales to some, whatever that limit is, which is in general not capacity. So there's still things you can improve. And the hope is that actually for these Reed-Miller codes, but it's not like we know how to do this, that the exponent might actually be optimum and that the limit, where the phase transition happens is also optimal.
All right, let's thank Rüdiger again.